Hi, welcome to this video. Do you like watching movies or playing video games that involve time travel, like Back to the Future or The Legend of Zelda? Have you ever wondered how time works in real life? How do we measure it? Why does it seem to flow in one direction? Is time travel possible? In this video, we will explore these questions and more, and see how time is one of the most amazing and mysterious aspects of physics and reality. Time is what a clock tells you. A clock is a device that counts how many times something happens over and over again. For example, a pendulum clock counts how many times a pendulum swings back and forth. A digital clock counts how many times an electric current changes direction. A stopwatch counts how many times a button is pressed. The standard unit of time is the second, which is based on a very special kind of clock that uses atoms. Atoms are tiny particles that make up everything in the world. Some atoms can emit light when they are excited by energy. This light has a very specific frequency, which means it vibrates at a very specific rate. A cesium atomic clock counts how many times this light vibrates in 1 second. This is very accurate and precise, because this light always vibrates at the same rate no matter what. We will start with the classical view of time, which was proposed by Sir Isaac Newton. He believed that time is absolute and universal, meaning that it is the same for everyone and everywhere. He thought that time is like a river that flows at a constant rate, and we can measure it with clocks. This idea of absolute time was very useful for describing the motion of objects and forces in Newtonian physics. We use time to measure how fast or slow something moves from one place to another. This is called motion. The speed of something is how far it travels in 1 second. The velocity of something is how fast and in what direction it moves. For example, if you walk 5 meters in 1 second, your speed is 5 meters per second. If you walk 5 meters in 1 second towards the north, your velocity is 5 meters per second north. However, motion and time are not the same for everyone, but depend on who is watching. This means that different people can see different speeds and times for the same thing, depending on how they are moving themselves. This is the idea behind Einstein's theory of relativity, which changed our view of time and space. One of the consequences of relativity is that time can stretch or shrink depending on how fast or how heavy something is. For example, if you were traveling very fast, like in a rocket or a spaceship, your clock would tick slower than a clock on Earth. This means that less time would pass for you than for someone on Earth. This is called time dilation, and it has been proven by experiments with clocks on airplanes and satellites. Another consequence of relativity is that time and space are connected, like two sides of a coin. This means that when you move through space, you also move through time, and vice versa. This also means that there is no absolute present, past, or future, but only relative ones. For example, if you were looking at a star that is very far away from Earth, you would see it as it was in the past, not as it is now. This is because the light from the star takes a long time to reach your eyes. However, someone who is closer to the star would see it as it is now, or even as it will be in the future. This is called relativity of simultaneity, and it shows that time is not the same everywhere. Time also plays a key role in quantum mechanics, the branch of physics that deals with the smallest particles and forces in nature. The main equation of quantum physics, called the Schrödinger equation, tells us how a quantum system changes over time. However, there is a problem. Time does not have a quantum operator, which is a mathematical tool that tells us what time does to a quantum system. This makes time very different from other physical quantities, like position or momentum, which do have quantum operators. This raises many questions about what time really is and how it works in quantum theory. Another interesting aspect of time is the arrow of time, which is the idea that time only goes forward, from the past to the future. We can see this in everyday life: eggs break, ice melts, people age, etc. These processes are irreversible, they cannot go back to their original state. This is related to the concept of entropy, which is a measure of disorder or randomness in a system. Entropy always increases over time, meaning that systems tend to go from order to disorder. The arrow of time is based on this principle of increasing entropy. Time also has a crucial role in cosmology, the study of the origin and evolution of the universe. The most widely accepted theory of cosmology is the Big Bang theory, which says that the universe started from a tiny point of infinite density and temperature about 13.8 billion years ago. This point is often considered as the beginning of time itself. However, there are other theories that suggest that time may have existed before the Big Bang, or that there may be multiple universes with different times. These theories challenge our conventional view of cosmic time. Finally, we will explore one of the most fascinating topics in physics, time travel. This is the idea that we can go back or forward in time by using special devices or methods. This is very popular in science fiction, but is it possible in reality? According to some solutions of Einstein's equations, such as wormholes, it may be theoretically possible to travel through time by creating shortcuts in space-time. However, this would create many paradoxes and problems with causality and logic. For example, what would happen if you went back in time and killed your grandfather? Would you still exist? Time travel remains a controversial and unresolved topic in physics. In conclusion, time in physics is far from a mere ticking clock. It is a complex and intriguing concept that has evolved from Newton's absolute time to Einstein's relativity and beyond. Our understanding of time continues to deepen as we explore its connections to motion, quantum mechanics, thermodynamics, cosmology, and even the tantalizing possibilities of time travel. Physics continues to challenge and reshape our perception of time as a fundamental dimension of the universe.